So generally, now I will start my presentation. And so if something is going wrong, so just don't be shy to shout. Otherwise, when I'm having a full screen presentation, I don't see your reaction, your responses. And clearly, you will see my face and I will see your faces after the end of presentation when we will have the question and answer session. So let's not now start the presentation. So I hope that you will see it in a couple of seconds. Is it visible now?
Not now.
Yes.
We can see it.
Okay, fine. Thank you very much. So I will start. You see the topic of the presentation. It is all about the new type of materials which are becoming more and more important for biomedical applications. So they're known as the printable polymers. And before I will start, I would like to acknowledge the contribution of my co-authors, James, who is now finishing his PhD, Dr. Elisa Mele, who is a senior lecturer at Department of Materials at Loughborough University, and Dr. Simon Lee, who is a senior lecturer in my group, and he is now present in this, taking part in this summer school. So you are all here because of this European Structural Integrity Society. I wouldn't do much of the presentation, but for all researchers, clearly it's of interest that it has a great tradition of publishing. Generally, 4 major journals: Engineering Fracture Mechanics, Theoretical and Applied Fracture Mechanics, Engineering Failure Analysis, International Journal of Fatigue. They're all publishing under the aegis of European Structural Integrity Society. And we have a relatively new development. It is Procedure Structural Integrity, which allows us to publish short version of papers of multiple meetings that our society organizes. Interestingly enough, it is now a proper journal in its own right, having even an impact factor. And if you have taken part in the virtual European Conference on Fracture, you can publish it there, and there will be also clearly publication of other journals. So the major activities of European Structural Integrity Society are organized through its technical committees. You can see here the list of them. And the one which is highlighted, it is the technical committee that I chair, which is organizing this first day of the summer school. So if you will look at all the other committees, they are predominantly dealing with the established and conventional materials, engineering materials like polymers, ceramics, concrete. Clearly, there is a lot about metals and alloys in other parts. Our technical committee, which was organized relatively recently, is the only one which deals with biomedical and biological materials. And the reason for this is that healthcare engineering is becoming a more and more prominent part of the engineering area, using the standard engineering approaches. But the materials that they're dealing with, biological materials and biomedical materials, they're not as good known as our traditional materials. So that's why there is a lot of interest in them, and everybody is welcome to participate in the activities of this committee. So if you are interested in this, here is a short list of activities. Clearly, we are dealing with the 2 major types of materials. On the one hand, these are more traditional materials, so like ceramics, metals and alloys and polymers, but which are used under totally different environmental and loading conditions related to the physiological conditions inside our body or related to it. So these are for implants or prosthesis. On the other hand, we are also interested in the biological materials in tissues. from the level of cells all the way to the tissues and organs. And this is very important to understand the behavior of this material under physiological conditions, as well as in their interaction with the medical devices, which can have totally different properties. And clearly, you understand that characterization of these materials is much more complicated than of normal materials. We cannot prepare a standard specimen from a bone or from a muscle, so just because the properties that we are interested in are those of a live person or an animal. So that's why there are other ways around this, but this is outside the topic of today's lecture. If you are curious, do join our events of the Technical Committee of the European Structural Integrity Society. And a very short announcement. We are also organizing from time to time special issues of the journals outside the remit of European Structural Integrity Society. For instance, at the moment, we have a special issue which is dedicated to damage and fracture of biomedical materials, published by the Journal of the Mechanical Behavior of Biomedical Materials by Elsevier. And everybody is welcome and have the time before the end of October of this year submit the papers related to this topic. After this introduction, let us start with an overview. Generally, I will give you a short introduction into polymers. So no offense for those who knows this, but it is still a summer school which attracts people with different backgrounds. So some of the topics probably can be known to people with the background in material science. Then I will go to the additive manufacture, and then we will discuss 3D printing of polymers. Let's start with this. So generally, the idea of polymers is pretty well known. They were becoming more and more popular in the 20th century, and now they are one of the major staple of materials used in various applications, and predominantly in the biomedical application, and this will be explained during this lecture today. The word polymer stems from the Greek language, which poly means many and meros mean parts. So this is a repetition of single building blocks. For instance, you have the ethene here, and then if they are being formed by the polymerization reaction, we will have a theoretically infinite line of these blocks, which is called polyethylene, which is pretty well known in our life. The use of these materials as biopolymers, they became these materials for such type of application more or less by chance. During the Second World War, for instance, in the airplanes, the parts of the airplanes, their visors, they were made of polymethyl methacrylate, known also as plexiglass or other parts. And the doctors, they've noticed clearly when the people were wounded, they found in the wounds, and sometimes the wounds were, for instance, in the cornea or in an eye, they found that generally, clearly, though the particles, they penetrated the soft tissues, but they did not cause any inflammation, any additional part of infection. So that was one of the starting point of their use. But speaking about polymers generally, they're going thousands years back. So some of them first were used in ancient Egypt. They were used, for instance, as lining sutures, so just also being used for some applications related to the biomedical to close, for instance, the wound. So why polymers? I already mentioned that we have so many different materials. One of the major reason is clearly that the properties, mechanical properties of these polymers, they are more closely related to those of the tissues. Their density the stiffness is not that far away or significantly closer than those of metals and alloys and ceramics. But this is not the end of the story. One of the important features is, as discussed with an example of PMMA, is their biocompatibility. They're also chemically stable, though sometimes it is the feature which we'd rather try not to use, but we can then change the properties of the polymers. The mechanical performance, as discussed, is close to that of different parts of the body. They can be easily blended together, forming different compositions with different properties. They're relatively cheap to produce. Their properties are pretty well reproducible. They have a good strength to weight ratio, which is important for the mechanical application, and they can be processed into different forms and shape. And 3D printed is a totally new application where these features, especially processability, are becoming very important indeed. So let us move to some of the polymers which are used for biomedical applications. And so just be careful, those of you who are planning to do a test today, because some of information will be used in this test. So polymethyl methacrylate was started to be produced in 1930s in the United Kingdom, and now it has a just broad area of application in orthopedics and dentistry. So this is, for those who like chemistry, its scheme, and one of the major properties, a beneficial one, it is biologically inert, and it has very good optical properties. So just I've mentioned, so just plexiglass, you pretty well know that this is pretty close like real glass in terms of their transparency. There are some downsides because of its so brittleness. It can damage some tissues, and it can also be affected, can be treated by the cooling when being deformed due to the heat generation in this process. So it can be used for different applications, but generally it can be used to bind implants, so like bone cement, and as plexiglass, it is being used for lenses. Another material is polyurethane, which started in 1930s, was first produced by Bayer AG in Germany. It is one of the analogs of nylon 66. And if compared to this known material, it has somewhat lower melting point, lower water absorption, and has significantly better mechanical stability. And there is quite a range of its beneficial features. So good fatigue resistance, mechanical performance, stable, biocompatible, and so just can withstand level of abrasion. And you can see here from a list of potential biomedical applications that it can be used for quite many different features important for surgeons and for the biomedical applications. Then we have polydimethyl siloxane, or simply known as Pdms. So this is its formula. It was developed in 1940s by Doe and Corning and General Electric in the United States of America. It is one of the most popular silicones that are being used in biomedical application. It is a thermoset, so just it cannot be easily shifted after and formed after it is being set with temperature loading. But on the other hand, it has high flexibility. It's quite durable and stable. As many polymers, it is also bioinert. And the problem with it, so just which can be either positive or negative, that's why it is neither green nor red. It inhibits micro, as a result of its hydrophobicity, it does not allow to microbes, so just as well as cells, to grow on its surface. And you can see here that it can be used for different applications, predominantly in the soft tissue prosthetics, and but also as artificial valves, drainage tubes, and so on. We are going now closer to our time. In 1980s, the polyether ketone, or PEEK, or PEEK, was developed in the United Kingdom. And this is a material which found quite a broad range of applications in this area. So the reason for this is that it is quite high strength to weight ratio, more than quite many metals and alloys. It have high temperature performance, so that's why it can survive, for instance, sterilization, very high chemical stability, and high resistance to deformation. So as a result, it is being used for load-bearing orthopedic application. So spinal cages, fixation plates, maxillofacial implants, screws, anchors, and so on. So it is a heavy loaded material, very important for multiple application as inside our body as implants. So then, we already discussed the polyethylene, and so it was developed in 1930s, also in the United Kingdom. And this material we pretty well know from our everyday life. Clearly suggests it can be used in different variants for biomedical application. Generally, its different forms are being considered based on their molecular weight. We can have a low density polyethylene, high density polyethylene, and we can have ultra high molecular weight polyethylene, where the molecules can have the weight of tens of thousands of the units. So, and as a result of its versatility, it can have different biomedical application. It has a very good toughness, so it's opposite to brittleness. So that's why you need to apply quite a significant amount of work or energy in order to tear it apart. So on the other hand, it have a low coefficient of friction, so can be used, for instance, in implants where there is a contact, for instance, in the hip or knee replacement. So just as a liner between the parts. So, and it have a high endurance. So just for instance, 90% of survival after 20 years in total hip arthroplasty. And here I need to comment that there, so just not many people understand that unfortunately the parts that are being put inside our body with a lot of efforts by surgeons, they're not there forever. So in many cases, they are lasting for 10 to 15 years, which seems is a lot of time. But you can imagine that if somebody is being exposed to this procedure relatively early in their life, then before their death, there can be several operations aimed at replacement and reintroduction of new type of the implants. And so just here are some of the applications which are generally already mentioned. Then we are going to PTFE. So just this is the name. So just in the morning, it's very hard to pronounce it. So I'm kidding, but you are pretty well know it's so just name as Teflon. So it is, just, there are some other variants. It is quite chemically inert, and this is one of the reasons for its application where the stability and inertness is needed. It can have good mechanical integrity, though so just under conditions of the constant load, it shows so just some deformations and creep can become a matter. So, and you can see here among the negatives, it it can absorb proteins, but cells do not feel very good on its surface. So this can be a problem. On the other hand, if we would try to avoid the just this kind of the growth of the biofilms on its surface, this is a very good positive. So, and you can see here as a result, it can be used not only in your kitchens, but also for anti-fouling coatings and different types, student catheters, grafts, meshes, such as so which are employing its useful properties. Then we are going to polyamide or nylon, so which was developed in 1930s by DuPont in USA, and it can be both suggest in biological form or can be synthetically produced. And it has, so you see here, no red, so mostly green line here, so that there are plenty of positive properties, very high strength, flexibility, toughness, chemical resistance, low friction, and additionally low cost. So as a result, it is also being used competitively with other materials in quite many biomedical applications, the main of which are given in the slide. Now we are going to polylactic acid, or PLA. So it was developed in 1920s, and it can be produced from the natural materials like corn starch, sugarcane, and the likes. And there are different isomers of it, all of them being used for biomedical application, PDLA, PLLA, and PDLLA. So generally here, interestingly enough, for the first time, we are putting as positive the possibility to biodegrade. And the reason for this is important. On the one hand, for some applications, we would like to put implants or any parts inside our body, and we would like it to stay there and to perform its function as long as possible. On the other hand, we do understand that this is something alien to the body, so we would rather prefer to put something only for some time and then to allow the tissues to grow and to take back their function. Clearly, we wouldn't like to put something, though sometimes it is being done, and then to make a surgery to remove it, so which is being done, for instance, with metallic pins. Here, after say around 2 years, if you put a stent inside the artery made of PLLA, that within 2 years it can fully degrade and can be removed in a natural way from our body, with the artery or nearly fully restored to its initial function. So, yeah, it is a brittle material, so suggest it has some problems, but it is generally there are suggest many positives, and it can be used for meshes in orthopedics. It also suggests some drug-eluting coatings can be put on its surface, and there are other applications. So we finished with the major classes of polymeric materials, and now let us go and to speak about the additive manufacture. Why additive manufacture, which is known by the 3D printing? The main reason for this is that we are all different. Our parts inside our body are also different in dimensions. So generally, the current development of the healthcare engineering is related with a personalized medicine. So clearly, in the ideal world, it would be rather to put not one of the few types of the implants or stents in your body as currently is being done, by rather to put something which will be like a suggest glove on your hand, specially designed and prepared by you. With any other technology, this seems impossible, but additive manufacture exactly provides this capability. So it was started several decades ago and was known also as rapid prototyping, allowing people to develop new components and structures quickly. But now it is quite a large industry with the world revenue of 6 billion in 2017, and which is to quadruple to 2023. And there are now quite many different type of machines being used, which are implemented different processes of additive manufacturing. We'll go through them relatively quickly so that you have at least an idea and understanding how it works. So, but all the processes have common stages. First of all, if you would like, for instance, to replace a part of a skull or to build something, you need to have a digital CAD file. This file is being meshed, so just and it is just this is a standard so-called STL file. Then this information is being transformed to the printing machine, where it is being converted into the so-called G code. And then this G code controls the movement or suggest of parts of this machine, which allows us to build any structure, any component, predominantly by building up one layer on top of each other. These are being produced by slicing the initial geometry and implemented in different ways. And here is, for instance, in my university, so just 8 years ago, we reproduced using this type of printing of the head or rather skull of Richard III. So just the skull was found close to Loughborough in Leicester around this time. So now we have the full skeleton of this so just British king. So I'm not going so just to dwell a lot about benefits, but generally in the nutshell, you practically use only most of the material that you need there. This is no removal of material. For instance, in machining, 90% is going into a chip. It's high level of adaptability, and so it can produce personalized solutions. So, and as a result, this is quite suitable for medical application. You can have bespoke parts produced by these and so just allowing personalized medicine. And so just clearly reducing animal test models if you produce the specific parts and so on and so on. So here are major features, but all of them more or less are aiming at building the different layers of the material and forming from the layers the full 3D structure. So the first historically in 1980s was stereolithography. So it is using the two-dimensional scans with the monomer photopolymer, which is being used inside the machine, and then the light or laser, it causes polymerization not on the entire domain, but selectively in only parts of it, building the structure layer by layer. It's have a very high resolution and geometric accuracy, but so just the monomer is not a cheap one, and it is a toxic one. So another point, so just to do this, it is material jetting. It's deposition of materials on top of the previous layers. You can consider this as, for instance, your standard printing, so just using an inkjet or laser jet when you are deposed on the sheet of paper different type of the inks, also just of powder, and causing later on the process of its solidification. Here, it is the idea, it is still using the droplet idea like with the inks, and as in the multicolored ink, it can be using different sources so that as a result you can form different parts made of different materials with different colors. So it can be based on the thermal principles or piezoelectrical principle. Then you can also use a binder jetting. So it have the foundation you can see here of a powder, and in the solidification of the powder, or rather not suggest, is achieved not by the melting and solidification, but rather binding it together with some adhesive, which is also being applied to a specific part of it. So suggest it can be produced also in different colors, but suggest it's generally as a result, its mechanical properties are not as good as other schemes. Then you can have what is now become more known as the selective laser sintering or selective laser melting for metals, but generally the common name is a powder bed fusion. You see that the scheme is not far away from the previous one. You have a bed with a powder, but here it is being solidified in case of the metal, so just by a laser, or it can be also sintered by the same laser, which is scanning on the surface, forming one layer at a time. Clearly, so just some of its advantages are related to its disadvantages. If you want to have a high resolution, each layer should be relatively thin in order to have fine features. So as a result, the total speed of production can be significantly lower, especially if compared to the mass production processes. So you can have also the methods which are now becoming also very popular, direct deposition of a material. Here you have a supply of the powder just into the process zone on top of the substrate or the previous layer, and then the focused laser beam melted together, forming a new part of this structure. So there are some benefits, but so just also the disadvantages, variability in the finish quality, and not all the materials can easily be used for this type of the process. There are the processes which are so just seems to be just more related to the more standard one. So you can see here rolls of the sheets which are being moved, and this is simply when you are putting the sheet on top of the previous layers, and then you are using ultrasonic solidification with the preheating if it needed, in order to consolidate only the parts of this sheet with the forming the profile in the cross section, which is related to this slice of a 3D structure. Then we can have a material extrusion. I wouldn't take much time about this because today, and it was supposed to be just after my original lecture at 11 o'clock, another representative of Loughborough University will give you the idea about the bioprinting, where material extrusion will be playing a significant part. But in the nutshell, this is quite a popular type of the printers. You can find them even in primary schools. You have a filament polymeric one, which is going through the head, being melted and deposited here. So, and there is an extrusion process being involved. That's why is the name. So it has a relatively high speed. The costs are moderate, so that's why everybody now producing something what they need for their hobbies. Also, just you can print the toys, you can print some missing bits of your appliances, and so on. Now we have the idea of the biopolymers, and we have idea of 3D printing. And let us look in the last part of the lecture, what are the possibilities as well as the challenges of the 3D printing of polymers. But before this, I would like to have a very general statement. As you can imagine, the entire processes, they are relatively new, and we are still in the very interesting and challenging time of development of both materials, which are printable, as well of technology. So that's why this is the reason for a high interest all over the world. And on the other hand, it is still a relatively large but still a niche area in research, with the properties of these materials being different from those produced with other technologies. So that's why a lot of activities, and there is a possibility for newcomers to go and to make your new research in this area. So these are generally some of the examples that you can produce using 3D printing. So some of them are so just more or less of often obvious ones. You can print a Pdms ear. So just, and some people are using this for cosmetic purposes. You can build an antibacterial polymer tooth, though honestly, in many cases, this is rather produced still not with polymers, but with the composites, if not with metals. But so just 3D printing can be used with metals, which is outside the topic of this area. Then, so you can see here some prosthetic sockets, which are being produced for different limbs. But these are only some of the examples being being used from the very large range of possible application. So going to PEEK, we've discussed it. So the process which is being used here, it is of material extrusion. You can see here an attempt which was performed at Loughborough, and so just to build a type of a scaffold, a porous one, to promote the proliferation of cells. But you can see immediately that something is not good here, and we have shown just also some examples here of the challenges that, depending on the temperature and the type of the process, you can have significant complications to produce the ideal geometry that you have built in your CAD file. So as a result of the thermal processing, you can see, for instance, a partial degradation, different level of crystallization. For instance, here, the dark regions are amorphous polymers, while the lighter regions are crystalline. And you can see that their distribution is relatively random. So another important feature, and this is what we are supposed to do all the time, we are always comparing the new technologies with those of the existing one, that the properties of these materials, they sometimes suggest significantly lower those produced, say, with the injection molding. And so just I would like to leave some time for the questions, so I'm going quickly through the other suggest parts of this. So for instance, we have the possibility to print the ultra high molecular weight polyethylene. But if you will look at the properties which are being produced in different parts, then they have a significant variability, with some having great properties, the others having mediocre one. Pdms for printing, so just to produce nice results is shown, for instance, here, but they should be printed into the some solution in order to provide a support bath for this. The properties also depend on the orientation of the printing materials, and you can produce quite many interesting results, but not all of them are having a good reproducibility on its different parts. The benefits, we can build, for instance, a very precise parts for the, as a substitute for the parts that we will need like to have in the body. And so just here is an example which I've shown that whether you are printed it on flat or on edge or upright, the properties would be different. And the final slide, which I would like to show you here, that all in all, we can approach most of the properties. Here, blue are for conventional polymers and red are for the 3D printed polymer. But so just in terms of the Young's modulus and strength, sometimes we have good match and even exceeding it. But sometimes, for instance, here we have a very poor variant of this. Clearly, it all depends to the process. So here, I would like to finish my presentation and with a statement that there is no conclusions. It's still a very, very early stages of the development, though we have already quite many achievements, but there are many challenges, and the way of the printing and the use of biopolymers in biomedical application is still the field of extensive development. Thank you very much. So I'm stopping my presentation.